So hello everyone, and thank you for joining us today. We're very excited to introduce to you a groundbreaking piece of software that we hope that you will want to try for yourselves. Now, by way of introduction, I'm an organic chemist by training who found his way into the world of NMR spectroscopy at a relatively young age and has stuck around ever since. So I know next to nothing about the mathematics of molecular modeling or structural dynamics, etc. However, I do appreciate the importance of having a deeper understanding of how a molecule hangs in three-dimensional space, or in the case of a drug candidate in a pharma environment, which conformation it prefers in aqueous solution. I'm sure we've all scrawled 2D structures on a fume hood window with a magic marker using wedges and dashes to indicate chirality. But when it comes to imagining how the whole molecule relates to itself structurally, I will wager that not many of us had the patience to sit down with their plastic modeling kit to build one. And even if we did, there are ambiguities about which way this bond goes and which conformation that ring adopts, leading inevitably to us staring at a single example from a larger set of possibilities, with no real confidence that we've built the one that actually exists in solution. Any decisions that we make when looking at those 2D drawings or that 3D stick model are therefore flawed by a lack of complete information. What I want to present today is a new plugin for Mnova NMR that we call Mnova StereoFitter that brings together all the tools that might be needed to enumerate which 3D conformation or 3D configuration is the most likely. The software was designed specifically with the chemist in mind and buries all the complexities of computational chemistry behind simple workflows. I will start with some historical context, then give you a brief overview of the toolset, followed by one of the many possible examples to illustrate the types of problems that this software can take on easily and rapidly on a standard PC. No special hardware required, nor a degree in computational mathematics. As far as we are aware, there isn't another tool available that puts so much power of analysis directly into a chemist's hands. StereoFitter is not intended to be a replacement for the experts. However, it gives a chemist a quick look-see for their own molecules that they're working on, before maybe working with their computational chemistry team on more in-depth investigations. It's a potential time saver. If the chemist can vet a set of molecules quickly, then any handoff to the project team's experts can be more informed. And it's potentially a cost saver too, because doing some of the work locally can allow colleagues with more expertise to spend their time on other projects. So where does Mnova StereoFitter fit into the bigger picture of analysis using spectroscopic data? By using Mnova, data from different techniques and from different vendors can be brought together to be processed and analyzed as a complete set of information. Usually, the first step is to determine the 2D constitution of the molecule. Mnova has many tools that allow the chemist to extract meaningful correlations in their data that all come together in Mnova structure elucidation to select the most probable 2D structure. From there, and prior to Mnova StereoFitter, this structure would be handed off to someone in the team that had access to 3D conversion and molecular minimization software. Now, what you can see is that Mnova StereoFitter completes the 3D structure search using NMR constraints as experimental evidence, but all within the Mnova platform. So here's a non-exhaustive list of applications where we think that StereoFitter will have a huge impact. So let's say knowing the 3D structure of a reaction product can inform about the reaction mechanism of how we got there. For example, did the reaction go SN1 or SN2? Academics, with an eye on technology as a way to show their students what they will use when they graduate into industry, will be very interested to create lesson plans using Mnova StereoFitter as a platform to teach how NMR information correlates to molecular structure. Whether academic or not, simply knowing which conformation or set of conformations that a molecule prefers in solution can be informative. And somewhat related to reaction mechanisms is the determination of relative configuration. Did I make the R or S isomer is a common question posed in a synthetic chemistry lab. And if at least one stereocenter can be relied upon, maybe from a chiral starting material that could not have been altered, then absolute configuration determination is also possible. And finding out as much as possible about what it takes for a ligand to bind to a target is what makes the wheels of pharma turn. And it is that last application for Mnova StereoFitter that conveniently lets me give a shout out to another webinar that is happening next month, hosted by the Brucker Pharma Applications team. Matteo will be joined by Armando to talk more about how StereoFitter can help with lead optimization. And Armando is the one at the top wearing a very interesting t-shirt. So you can register by visiting the link shown on this slide. So let's start with some context. Scientists have been trying to determine 3D structure of molecules, large and small, for a long time. Methodology evolved rapidly as NMR magnets got larger, NMR spectrometers got more powerful, and computing power exponentially increased in capability. In the world of macromolecules, we even gave it its own field of study, structural biology. Breakthroughs in medical science have come about in many ways due to the relationship between structure and function. In the small molecule arena, it has been more of a stop-start timeline. Molecular modeling software for small molecules has been around for just as long as it has been for proteins, but nothing really emerged that brought it all together under one roof when compared to, say, the CCPN initiative for biomolecules. Now, as you saw on the first slide, StereoFitter can use NOEs, residual dipolar couplings, scalar coupling constants, and predicted chemical shifts as experimental evidence. Here I will go through each constraint type and highlight the movers and shakers in the field, because it's important to remember that we all stand on the shoulders of giants when we go about our daily work. So let's start with the nuclear over-Hauser enhancement, or NOE. And if we're going to start with how the macromolecule work uses NOEs, then we have to mention Kurt Voutrus's book from 1986 as the book of Genesis that started it all. Many types of NOE techniques have been discovered, and Nee's paper in 1994 summarizes those quantifying the NOE response for structural work. Mike Williamson wrote a nice review in 2009, and the picture at the bottom is from that review. It shows that with an increased number of constraints, then the definition of the 3D structure becomes more accurate. Switching to small molecules, we also have to start with a book that every self-respecting NMR spectroscopist has at one time or another sat down and tried to digest. I know that I certainly learned most of what I know today about NOEs from David Neuhaus and Mike Williamson's book, whose first edition was actually written in 1985. Mikura published a comprehensive paper on all sorts of NOEs for small molecule analysis in the very early days, and I picked out a picture from that paper that you can see here. From the NOE measurements, it was apparent that the molecule formed a cylindrical 3D shape, which I found quite interesting. So what is there to say about using scalar coupling constants as constraints for 3D structure? This goes all the way back to the year dot with Karpus's work, later generalized by Altona. At the bottom, you can see a graphic from Altona's paper, which I'm sure many of us have scribbled something similar when trying to figure out why our proton NMR had a weird coupling constant that initially didn't make sense until we figured out the dihedral angle. Turning to residual dipolar couplings, Jim Prestegard, while he was at Yale way back in 1995, was probably the first to publish. He looked at myoglobin, which has a high anisotropic susceptibility, which self-aligns in buffered water when placed in the magnetic field. Now, not many proteins have a paramagnetic anisotropy. Most are diamagnetic. So Nico Chandra and Ad Bax followed up in 1997 with maybe the first of 1,000 papers that picked ubiquitin as its example. Diamagnetic proteins don't self-align in the magnet, so they need help. And that came in the form of DMPC-DHPC phospholipid bicels. Now, if you want to start somewhere here, then I highly recommend the review article by Kang Chen and Nico Chandra in 2012. The picture is from Prestegard's paper and shows an HSQC of a nitrogen-enriched protein with coupled amide signals. Now, the graph is from the same paper and shows calculated versus experimental RDCs. There were no fancy graphics back in the day, and so proof of the best fit was a convincing correlation coefficient. Residual dipolar couplings for small molecules is as old as the hills as well. Small molecules tumble rapidly in isotropic solution conditions, so the chances of extracting RDC values without some form of intervention is approximately zero. The first attempt to try to get them aligned into an anisotropic condition was to dissolve them in a nematic solution, that is, solvent molecules that line up with the magnetic field. Sauper was one of the first to publish, and he chose benzene as his example. The top proton spectrum is benzene dissolved in a co-solvent, and the bottom spectrum shows 72 lines for the benzene molecule alone when dissolved in its pneumatic solvent. The lines are sharp, but as you can see, they are spread out over thousands of hertz. So it soon became apparent that any small molecule with a non-symmetrical structure of any interest was going to be intractable to analyze. More recently, and by that I mean in the last 10 years or so, there's been a great leap forward in the ability to partially align small molecules in solution by the use of polymers. Now, the first wave came when polymer molecules were added to a solution, and you can see 3 examples here, much like the bicels that were added to the solution of ubiquitin. Their presence restricted the rotation of the small molecules just enough to allow RDCs to be observed. And more recently, a second wave of polymer gels have been engineered that are cross-linked, so they can act as a kind of Swiss cheese, where the small molecule can still float around isotropically in the voids. However, when stretched or compressed, the voids become smaller, which rotationally restricts the molecule of interest, such that partial alignment can be observed. And the beauty of this technique is that the amount of alignment can be tuned by the amount of physical stretching or compression, up to the point of failure of the gel. In the picture, you can see that when dissolved in the solvent, the gel swells considerably, and so when placed in an NMR tube, it completely fills the inner space of the tube prior to deformation by stretching. This can happen within a few hours, so it's a practical technique. And for the best review article I've read, start with Volker Schmidt's review in MRC. And finally, we come to the use of predicted chemical shifts as a constraint for 3D structure conformation. This is the new guy on the block, chronologically speaking. Not that the theory hasn't been around for a long time, it has. It's just that it's taken a longer time for computers to evolve to be able to carry out the intensive number crunching required to make the density functional theory calculations possible in a non-prohibitive amount of time. There have been chemical shift calculators around for a very long time that only take into account the bonded nature of a structure. But as we all know, that is not how the real world works, and chemical shifts are as affected by through space effects nearly as much as they are by through bonds. Now, the picture at the bottom is the simplest one I could find that nicely hints at how chemical shifts could be affected by ring currents of neighboring aromatic rings in different orientations. David Wishart at Edmonton University in Canada is probably the most well-known in the protein NMR world to contribute in this area, and one of his many papers are listed here. But for small molecules, we had to wait another decade or so, and this paper from Armando is a good representation of where it all started. Well, does it work? It sure does, and here are just 2 examples of peer-reviewed papers in Jackson Science that have beaten a path for the others to follow. So let's quickly go through a number of the major features of StereoFitter before you see it live later in a demo setting. Now, as you can see, the tool set is delivered as a dedicated ribbon on the Mnova user interface. Let's start at the beginning. Now, while it's really easy to draw your own molecules using the molecule ribbon in Mnova, if you do load external structures, whether they're 2D structures or 3D structures, then the numbering system of the incoming structures will be changed to that of any that are already loaded in the compounds table. This is an extremely convenient tool because external programs tend to use their own atom numbering schemes. And before StereoFitter came along, one would have to transpose numbering systems manually before importing. So there's a massive time saver right there. This is a bit of a gotcha in that the next tool I want to show you comes with Mnova itself and not with the StereoFitter module. And that is the 3D conversion tool, which will take any 2D molecule in the compounds table and convert it into a single 3D molecule. So once again, if you don't have access to external software that can do this, then the tool's right here. Now, as I mentioned earlier, if you do not have access to external molecular mechanics programs that can generate sets of conformations, then you can do that with either of these tools built into StereoFitter. If you have a 2D molecule that has implied chirality, then the Generate Stereoisomers tool will list all of the possible stereoisomers possible, including enantiomers. It places them in a window where the chemist can trim the list with a delete button and then pass them over to the compounds table for further analysis using this button. The 3D molecule window is an interactive pop-up that allows the chemist to inspect 3D structures. There are lots of features in here, some of which I'll touch on in the demo later. The 3D correlations window is where StereoFitter really packs a punch and takes all of the legwork out of extracting constraints from NMR data. On the left, you can see a window that contains NOE information, and I'll touch on that more in the demo section. And on the right is the RDC picker, where one can simply drag over pairs of peaks in the isotropic and anisotropic spectra, and StereoFitter figures out all the splittings and the residual dipolar couplings for you. Now, prior to StereoFitter, all of this information had to be extracted manually from the spectra, RDCs calculated in a spreadsheet, and then input as a text file. And I wanted to touch briefly on StereoFitter's ability to calculate DFT information. If you don't have access to an external packages that can do these calculations, such as Gaussian, then it's available right here. The calculator is hosted in the cloud on a Mestra Labs server. And once the DFT results are sent back to Mnova, then it's pretty much instantaneous to calculate the proton chemical shifts, as well as the carbon. So how does StereoFitter calculate the best fit from the available conformations and experimental constraints? Well, we use the Akeiki information criterion, or AIC, which ensures that the model doesn't overfit the data. A quick look at the picture at the bottom shows 3 graphs. The one on the left is less than useful, as it doesn't use enough of the evidence to draw the line. The one on the right goes too far, and this is a classic case of overfitting the data. In the middle, we have the perfect balance, and the fitted line is a good representation. AIC does this for us by rewarding the models that fit the data, while penalizing those that use too much of the information, which is the overfitting. StereoFitter will iteratively run models, starting from the simplest one conformer model, each time calculating the AIC score, and adding more conformers to the model, knowing that the score will be penalized, and this will continue until a minimum AIC score is reached, whereupon the calculation stops. It doesn't calculate every single possible model, as other fitting routines are prone to do, and it so is extremely rapid in its execution. Now, this is the only slide with any mathematical equations on it, I promise. But what it shows is how StereoFitter can combine constraints from all 4 NMR techniques, if available, to calculate a chi-squared penalty function for a model, using as many of the available conformers as it needs in any weighted combination. Normally, this would be enough, and the lowest chi-squared would be sufficient to identify the best model. However, this is only half the story. What the Akeiki information criterion adds is a crucial piece that takes into account the number of models that make up the chi-squared value. If there are more models, represented by n in this equation, then the AIC score will increase. So the best fit is the one that has the lowest chi-squared, but also the one with the fewest number of models when chi-squared values are similar. And so StereoFitter uses the AIC score to identify the best model. And just as a bit of levity, here's a nice little paper that uses AIC to fit wine prices to wine ratings that we see on bottles in the store, which just goes to show that people would do anything to get a free drink while supposedly doing science. Now, StereoFitter may be the newest software that claims to calculate 3D structure, but it certainly isn't the only game in town. If you have deep pockets, then there are professional services out there that will take your 2D molecule and deliver you a 3D structure with some justification of their results. There are also software packages that complement what StereoFitter can do, especially when it comes to molecular mechanics or DFT calculations, and some of them are listed on this slide. However, it's MSpin that needs to be called out because of its natural relationship with Mnova StereoFitter. MSpin was conceived by Armando Navarro Vazquez when he was at the University of Santiago de Compostela, which coincidentally is the hometown of Mestra Lab research. It was there that Armando struck up an academic relationship with Carlos Cobas, Mestra Lab's president, and from that, MSpin was born as a standalone program in 2009, marketed by Mestra Lab. Now, it's our belief that MSpin was the first commercial software that could handle RDCs for small molecules, and which later evolved to handle the other NMR constraints as well. To run MSpin, one has to provide all of the constraint information as a text input file, which can be quite tedious if there's lots of information. And as you saw from the previous slides that showed its toolset, Mnova StereoFitter is the natural next generation software from MSpin. At the risk of repeating myself, and before I move on to the demo section of today's presentation, I just wanted to go over the similarities and differences between the conformational analysis and configurational analysis available in a Mnova StereoFitter. So let's start with conformational analysis. For this workflow, we only require one molecule, for which we need a set of possible conformations. As I described earlier, these can be calculated within StereoFitter, or they can be brought in from outside. And so here we have 3 conformers for a single molecule. The set of conformers are fitted to the experimental evidence in the form of NMR constraints, and the result is a best fit for the evidence, which might actually be a percentage contribution from more than one of the conformations. Now, if we look at configurational analysis, we start with more than one distinct molecule, in this case 2 diastereoisomers. For each stereoisomer, we need to have a set of conformations, just like you saw on the previous slide. Now, when we let the calculation loose, this is going to take each stereoisomer in turn, do a conformational analysis, and compare the best fit model between the 2 isomers, and present that as a result, as you can see in the histogram on the right. The right-hand bar on the histogram is the lower AIC score for the R isomer, and that AIC score is computed from a percentage weight from 2 of its conformations, as you can see on the bottom right. So in essence, a configurational analysis is a superset of conformational analyses. Okay, so now I am going to switch over to the demo, and I'm going to show you one of the many problems that StereoFitter can very easily solve. So what you're looking at now is Mnova in its new modern user interface configuration, and at the top here is the StereoFitter bar, ribbon bar, with all of the tools. Now I've preloaded a spectrum of quinine, and quinine has all the explicit hydrogens added. And what we have for NMR data is a proton spectrum and a nosy spectrum. So in this particular case, we're only going to use NOEs as our NMR constraint, and we'll see how we can match up some conformations. Now I'm not going to go to the trouble to generate those conformations, they've already been loaded. So if I pull up the 3D molecule window, I can interactively play with the molecule. Now the font's quite small on the resolution on my screen, but down in the bottom right-hand side, I'll tell you that that says number 1 of 14, meaning that we have 14 conformations inside of this 3D molecule window, which is actually built or stored within inside this molecule here in the compounds table. Now I can go through the series of each one of these quite quickly and easily. So you can see the first one is 87.35. These are all ordered in order of energy. So as I go to the second one, you can see that this methoxy group is starting to move around. Let me just go back to number 1. Okay, so you can see we're moving through them. And if you see the second one is a slightly higher energy, and its population of all 14 is 25.66%. And if I go back, the first one, the lowest energy is 58.88%. And so we can move all the way through this if we like. So if I just go to the last one, which is number 14, down here it says 14 of 14. You can see that the energy is actually really high now. It's 12 or so kilocalories per mole higher, and its population is effectively 0. Now we can decide at any point before we do the calculation that we can trim or we can extract conformations from this list at will. And so I'm going to take out number 14 just selectively by going to the delete button and just clicking current. And by doing that, I'm going to delete number 14 from the series. Okay, let's spin that back around again. And now down in the bottom, you've got number 1 of 13. So now we've got 13, and it's reset itself back to the first in the list. So we're back looking at the first one. Now 13 conformations, that's fine. We can work with all of those, and we can work with more if you like. Calculation just take longer. But for the purposes of speed, I'm going to show you another conformational selection criterion where we can do delete by energy level. So what I'm going to do here is pop up this window that says delete all conformers with energies exceeding the minimum energy conformer. That's this number over here, plus the delta value. Now I've just arbitrarily chosen anything above 3 kilocalories per mole. So anything above 90.37 will get deleted from the series of 13. So if I click the OK button, down here it says 1 of 4. So it's pulled out all but 4 of those conformations. And if I can just show you, you can just still see the conformations. So what we've done is we prepared the set of conformations that we believe to be credible, which we believe to be representative of real life and solution in the tube. So that's part 1 of what we need to do. Part 2 is the NMR constraints. And so here we have a pre-picked and pre-integrated nosy spectrum. It's assigned as well, so the proton spectrum is assigned. And as I mentioned at the very top of the presentation, there are lots and lots of tools within Mnova which allow you to get to this point very quickly. So once we have an assigned nosy spectrum, and each of these cross peaks are present in the assignments table already, then what we need to do is assign or calculate distances for each of these volumes. And we can do that really easily within Mnova StereoFitter. And this is, as I said, is where the Mnova StereoFitter really shines. So I am going to pull up the 3D correlations table just quickly. And what we're going to do is we're going to fill this table with all of the information on that nosy. So we get a column of distances over here. Now, before I do that, if you've read your David Neuhaus and Mike Williamson book, that's the first one I ever read, which said you can calibrate all of the distances with the volumes by picking a fixed distance or a reference distance in your molecule. So I'm going to pick this hydrogen 41 to hydrogen 14 in this pyridine part of this bicycle. And I know that in literature, I can find that, and I can find good values, and I can set that. And so the way you set that reference value is by popping up this options window, where I can set number 43 to hydrogen 41, again, it's just over here, to 2.46 angstroms. Now, I could have also used the 3D molecule window to show me the distance between those two protons if I didn't have literature. We also have 2 ways of using those numbers, those cross-peak integrals, either the peak heights or the volumes, when we use that 2.46 angstroms as a calibrant. So let's put that away. So you're going to have to do that once. Now for this table, you can, if you so choose, interactively pick nosy cross peaks one after the other. But why would you do that if we have a button that says fill the NOA table automatically? So let me click that. Okay, that's just saved a hell of a lot of time compared to what used to happen or used to be available. We have a table which represents the nosy data in a different form. So what they're saying here, just go to the first row. So hydrogens 27 and 30, which is a CH2 group in our molecule, is connected to hydrogen 29 through space, which is a CH. It tells me where that cross peak is if I want to refer back to it on the spectrum. And then we have cross peak volumes and also which of the values it's using, which I'll come on to demonstrate to talk about in a second. And then we've calculated distance here of 2.69 angstroms. Well, where did that come from? So if I just scan down to the bottom, you can see this line in bold. And here we are, we've got 41 to 43, both CHs, and theirs it's being set to 2.46. So that previous pop-up is our anchor point for the rest of this table. Now in this particular case, it only used one of the cross peaks, and that's because if the two cross peaks are different by more than 10%, it's always going to pick the bigger one, otherwise it averages the two. So that means that this cross peak has been influenced by something in the spectrum which has caused its volume to go down. So as I say, it'll only pick this one, and that's reflected in this box here. So it's going to use the diagonal peaks and cross peak number 2. Now if I just leave that pop-up over the top, at the bottom of that pop-up, it talks about the panic technique. And so the panic correction technique has also been built into this nosy analysis. And for anybody that doesn't know what the panic technique is, this was something, well, the phrase was coined by Krish Krishnamurthy, but it refers back to a normalization of the cross peaks based on the diagonal value. And why would the diagonal values be all over the place? And that's usually to do with either cross correlation or the mixing time being set wrong. And so in essence, the panic correction corrects for the mixing time and any other artifacts so that your cross peaks are normalized. And so we're going to use this value to calculate all of these values. Right, so that was pretty quick and pretty easy. This is a scratch pad. As I say, you can actually go in and you can calculate, you can change some things. So, I mean, you can choose, even though it's picked them automatically, you can choose different cross peaks. And so now what we want to do is transfer this information into the assignments table, because it's the assignments table that the calculator actually references. So if I go to the bottom, and once I'm satisfied with which rows I've picked, I've done all the editing I want, I click the Save 3D Correlations to Assignments table. That automatically pops the assignment table to the front very conveniently. And so this is my assignment table in which actually I've only got chemical shifts. I've only assigned the proton spectrum, so there's no chemical shifts associated with any carbon spectra. And in a new column called NOE, you can see that these distances have been transferred from this table into this new column NOE. And because hydrogen 25, it turns out, is actually connected in space to two different protons, it has two differences. So it's connected to 29 by 2.62 and hydrogen 41 by 2.98. And so therefore you can see multiple instances. And it's this set of distances that we use as an ensemble in the calculation to try and fit to the experimental evidence, to the conformers, the set of conformers. Okay, so let's do that calculation. So the first thing to do is set up the calculation because there are a number of options. Let me just pop the options up. So we can use the AIC method. Now the checkboxes here are all empty because, as you can see from the table, the predicted chemical shifts information is empty, the scalar coupling constants are empty, and the residual dipolar couplings column is empty. And so we can actually check these boxes and nothing's going to happen. But if you actually had more than one technique available, let's say you had some scalar coupling constants as well as RDCs, you could choose to include them or exclude them during this stage. So we've only got NOEs, so let's click that. And now we're just going to run the calculator. And that's how quick it is. That's in real time. So what's just happened? It's just popped up two windows. It's popped up our friend, the 3D molecule window, so we can inspect the different conformers that have been selected. And it's popped up a new StereoFitter results window. And here you can see the results of this calculation. And you can see that the lowest AIC score is actually a mixture of conformer 1 and conformer 3, but not 2 and 4. And it's actually a mixture of 55 and 45%. Now, if we go to the next one, the next highest AIC score, you can see this actually added in a tiny amount of conformer 4 with that very almost similar 1 and 3. And so, you know, maybe they're really the same, but it just shows you that the calculator will actually pick out different possibilities. And again, in solution number 3, which has 3 conformers, hence it's got a bigger penalty function in the AIC, there's conformer 2. So I'm pretty confident from this result that if I was going to write a slide and show my boss, I would say that the calculation said it's 55% of 1 and 45% of 3, sorry. Now this is interactive, so I can click on conformer 1 and it will pull up conformer 1, and I can pick up conformer 3 and conformer 3 will be shown, and I've got full control. And finally, what I want to show you is that if you go down to the set of NOE distances, as I just hover over various lines in this table, over on the left, you should be able to see some red spheres. And so that particular one there, between 26 and 42, is probably one of the crucial NOEs one would want to see to make sure that that top ring is connected to the bicycle at the bottom in this particular orientation. If I go to conformer 1, the calculated changes, but the experimental stays the same, and I can do the same thing. Okay, well, I hope you appreciate that that was pretty quick and easy. A simple nosy spectrum, a simple set of conformers, pull them together quickly in the 3D correlations table, save them to the assignments table, and just run the StereoFitter, and you get the answer. So in summary, I hope that we've successfully shown that Mnova StereoFitter offers a comprehensive set of tools for 3D structure determination. It's simple to use and all integrated in the Mnova platform. So it's possible to take a flat 2D molecule all the way to a preferred 3D structure. And so with that, I thank you for your time and attention and hand it back over to Enrique.